Welcome everyone to another Spectre update here, the for some years already known security vulnerability. And what is new is just disclosed the other week, branch history injection. So what this means is that latest Intel and ARM CPUs are again affected by this. That is CVE 2022-1. Matching there, and 2 for the Intel side, plus on ARM that is 23,960. How many security vulnerabilities can you have? On the ARM side, basically everything modern is affected. On the Intel side, obviously 2. So what is it? Previously we had this already here on this channel as well. That is a class of transient execution and basically timing attack speculating bits out of hidden private state, either from operating system kernels and JavaScript engines, for example, and other just-in-time code, and basically everything in between. And previously Intel and ARM provided hardware mitigations for that. And here on Intel IBRS. And what this new research unfortunately shows is that those hardware mitigations are actually, again, vulnerable, right? The revival of cross-privilege Spectre-v2 attacks on modern systems deploying in hardware defenses. And as they write here somewhere, that, where was it, somewhere here, so yeah, modern Intel CPUs provide that, right? And as seen here, upon Spectre disclosed software vendors such as the Linux deployed stopgap mitigations in software red lines, and maybe we take a look at that in a second. And also, yeah, spoiler alert, AMD is also affected, right? In a different way. So it turns out, so this new disclosure here of security research is like, hey, Intel and ARM, right? But what is with AMD? So AMD didn't implement this hardware mitigations in full anyway. So due to that, the performance of that was not outstanding, and AMD didn't even recommend this. But it turns out Intel of all has, it sounds a little bit like, hey, we have a bug there at Intel. Let's take a closer look at the AMD side. And so to me, it's a little bit like, Intel security researchers of like, hey, wait a minute, but AMD has also some issue, right? So it's like a little bit finger pointing there. But credit where credit is due, the Intel security team Storm has found that. I slightly wonder why sure, if you have this outstanding high performance silicon, it's probably logical to analyze also your competitors' solutions or the lack thereof and analyze this in detail. And if you analyze that already and you find issues, to also disclose that. Not only for AMD customers to get their mitigations, but also certainly a little bit of pinpointing of this AMD stuff also not outstanding and has issues. Because they found what the AMD recommended solutions, so there were generic red polines and there were AMD polines as well. I'll see that in a second again. And turns out that the Spectre mitigation approach, and this also means like basically all the AMD stuff in production that until last week also had run this AMD recommended AMD polines. Actually need to check if they call it like that. Were actually not fully mitigating that, right? So much to AMD's like, hey, we have a little bit different and higher performance solutions, like, yeah, wow, that also wasn't secure. So yeah, while Intel processors were recently found to still susceptible to Spectre-v2 based via branch history injection, despite the company's use of enhanced indirect branch restricted speculations, EIBRS and or red pill mitigation, the AMD alternative mitigation, so studying alternative mitigation techniques and several other options, varying level of performance trade-offs. Intel says its ecosystem partner asked the company considering using AMD's L-fence jump technique mitigation in a red pull-line alternative, commonly referred to AMD's red pull-line, which I wrongly refer to as AMD pull-line. The correct name for that is AMD's red pull-line, aka my short form of AMD pull-line. Anyway, the result of Intel's investigation, company discovered that the mitigation AMD has used since 2018 to patch the Spectre vulnerabilities isn't sufficient. The chips are still vulnerable so much now. Also, yeah, this stuff is so complex that it takes 3 freaking years of the brightest and the best of the industry to find out what the stuff we were running, not only initially vulnerable and insecure, but also the vendor proposed mitigations also not sufficient. That means also this had to be reworked, and I slightly wonder, maybe in the Linux kernel AMD is now also falling back to generic red pull lines, which have some performance impact. Anyway, so it was always known that the fast forward a couple of years, and Intel and ARM released efficient hardware mitigations that are not fully mitigating. Efficiently not mitigating. To prevent such trivial BTI exploits, the solutions are complex. Read those papers there, and we will see them. We take a look at this paper, and I summarize this here relatively quickly in probably 30 minutes. And yeah, of course, if I summarize this years of research in 30 minutes, it's still complex and long story. Long story short, those gist of them is that the predictor somehow keeps track, so that is the hardware predictor somehow still keeps track of the privilege level, user kernel in which target is executed, and as you might expect, the target belongs to lower privilege level kernel execution won't use. For example, more arbitrary attacker provided code locations to speculatively hijack the kernel control flow. And so it was previously known, I think, I was here, so much I probably should make better notes in the future. It was known that those, wherever they mentioned that those hardware mitigations do not cover all details, but it was deemed to be sufficient. But as this research has shown, of course not. So that is the paper here, branch history injection. So this is, I probably should have changed this differently, also maybe like that. So quite some papers of this research paper, so with, yeah, whatever. Quite some papers. Maybe I should have actually opened that in here to see the freaking, 18 pages, the usual research stuff of the University of Amsterdam. And as you see from these papers, the stuff is complex. Right, first the summary, and the stuff was vulnerable and hardware mitigations and stuff. And they introduced branch history injection, BHI or Spectre-v2, branch history injection, new primitive to build cross-privileged BTI attacks on systems deploying isolation-based hardware defenses. Like this Intel and ARM mitigations, on their observation that while the branch target state is now isolated across privileged domains, such isolation is not extended to other branch predictor elements, tracking the branch history straight, ultimately re-enabling hardware mitigations, but ultimately re-enabling cross-privileged attacks. They further analyze the guarantees of hypothetical isolation-based mitigations, which also isolate the branch history and show that, bearing a collision-free design, practical same predictor mode attacks are still possible. To instantiate their approach, they present an end-to-end exploit leaking kernel memory from user space on intersystems at 160 bytes per second. So this stuff is not super fast, right? And welcome everyone. Also comments already, Linux patches for that. Yes, I think the Linux patches for that are in 5.16. Oops, thanks for asking. Where's my focus? Yeah, I think the patches for that are in 5.16, and I think .14 also has some more mitigations, at least mitigate Spectre and stuff. But I think the base stuff is in 5.16, but don't quote me on that. Here's I also have a video, so just to show you how this is just their presentation video. So this stuff is time-consuming, right? So they write there 160 bytes per second. And I also wonder if you could potentially detect such attacks with monitoring CPU load and system call utilization. But so what they show here, of course, they could have just Hollywood-style PowerPoint presenters, but you probably can run the code. But what this basically does is Bruce forcing that also here, like 8 minutes. So this stuff runs in 8 minutes. So it's not like, and you have your etc shadow hash. So this stuff is running on 8 minutes on Core i7 10700K, but eventually after 8 minutes, it is computational expensive, but in the end, after 8 minutes of local execution time, actually, can this not stay like here? 8 minutes later, you have your password hash. So the stuff is real. It is computationally expensive. It is as previous. It is simply complex to timing attack that in that detail. I said 2 years ago, I think, that I'm surprised that this stuff even works. I mean, obviously, even Intel engineers were surprised. Or Intel, basically the whole industry of hardware engineers were surprised that this works, and I'm still surprised. Certainly amazing and outstanding research. So 160 bytes per second, in spite of the existing hypothetical isolation-based mitigations, conclude software defenses such as red lines remain the only practical BTI mitigation. So that means basically Intel's implementation, recurring theme, right? The stuff is so complex and error-prone, and why we need somehow more open hardware and research, because it basically took half a decade of research to come to that, and even then, the vendors like Intel and ARM implement hardware mitigations that, like, a year or two later, it's like, yeah, YOLO, those defenses, like, yeah, they're for the trash can. So now we have Intel CPUs or ARM CPUs with hardware-based mitigations that are basically wasting silicon and are pointless, as they show that foreseeable future, the pursuit for efficient hardware mitigations must continue. So this stuff, as per usual, you can read this. I read this actually yesterday. The problem is even I read it yesterday and half of the details I forgot already. But basically, simplified diagram, right, of indirect branch prediction, logic branch source address, and various branch target buffers and stuff. And they also have a fancy table, right? So long story short, you still need those software mitigations. They also have a generic. So the software defense is generic red line ground into standard software defense against BTI, return stack buffer. The red line traps into an infinite loop and possible speculations until the actual address is resolved and popped from the stack. As a result, no indirect branch prediction is performed. While red lines is documented to work on most Intel and AMD systems, it's not effective on ARM. And the AMD red lines, also which we see later in the other research, were not fully effective. Proposed an alternative red line defense where every indirect branch is turned into an L-fence jump sequence. The L-fence ensures that the load from the indirect branch target is retired before the jump, masking the residual transient window small enough to hinder exploitation. The solution is tailored for AMD processors and performs better than generic red line. So I think this paper is brand new and I think already outdated. So this is like, yeah, YOLO, this actually wasn't really mitigating it fully. And so the hardware defenses, Intel AMD IBPB, indirect branch prediction barrier, is a strong barrier to ensure that the execution, as they also see, this is actually here Where did they have that? Not in the fullest form of EIBRS implemented on AMD hardware. So this is why AMD previously still recommended the AMD red lines, which the next research has found also not to be fully mitigating. They also have here ARM defenses, even Google, Tensor, Cortex, and Qualcomm Snapdragon. And as you see in this table, various models, microarchitectures, software and hardware defenses, availability, and recommended by the vendor and not affected by this BTI, branch history target injection. Yeah, bypassing this, not sure if it's worth to go into the full detail of that. It's actually pretty complex for computer scientists to follow. Basically, the long story short, run the latest operating system updates. And maybe leave in the comments below how much more detail we should discuss this, because the implementation detail of all the jumps and history buffers and stuff, attack surface and such, is rather complex. Even here, understanding BHI on Intel, for example, I only wonder if you can actually use modern. I wonder if it would be better to redesign operating system call implementations to better mitigate this in the future. Think Linux IO Uring, because I would think due to those not being direct system calls and executed indirectly, I would think such a system call path should be not subject to this kind of speculative execution. And with that, I wonder if it would be better going forward designing operating system call architectures fully asynchronous there. I didn't take a full look into this. This is certainly difference of my channel and others just presenting that. Maybe I should also leave in the comments below. The problem is maybe I should make better diagrams and make a 20-minute sophisticated presentations. But the problem is to make a 20-minute distilled presentation, I need like 3, 4, 5 hours that I don't really have. But synchronous kernel C++. I recently was made aware that there is some research kernel Managram full asynchronous OS based on modern C++. I'm not saying modern C++ is a solution. I'm only saying I didn't take a look into the system call interface from this is Managram. I didn't fully research this. I only booted that. I probably should. You probably want to share, like, and subscribe, because I currently simply don't have more time, right? In this pandemic, keeping my company alive and feeding the family and taking half of the day care of, without child care of, entertaining our junior. They claim a full asynchronous implementation, and I looked into this, so some details I'm not fully impressed with. However, I probably should take look into that implementation details. In some ways, some things sound interesting. If it is implemented, they write here, based on microkernel or common desktop operating systems, we obviously know that, uses completely asynchronous API for I/O despite those internal differences. Managram provides good compatibility with Linux kernel, and microkernel slow, performance disadvantages, and so on, providing good abstraction, efficient implementation common. And so I wonder if, again, I didn't take a look into that. I only wonder if not only for performance, right, as seen as Linux I/O Uring, of having as the name implies, an ring buffer of I/O commands, and even using that on monolithic Linux kernel to vastly improve I/O performance. Again, I would need to research what exactly they implemented there in Mana GARM. But yeah, if this is fully asynchronous, I wonder if this still implies, because for this, my understanding is you need quite some precise timing attack here. And if you run this stuff fully asynchronous, I would believe that this direct branch execution channel would be fully mitigated. But yeah, leave in the comments below. Maybe I should research that in more detail. But that is my high-level understanding, that there's potentially so much to reinventing the wheel, or actually more innovating in more drastic ways over 30, 40-year-old system call implementations and modern things. Because I would say this is also the thing, right? Intel spent, or Intel, ARM, and AMD at times spent hardware mitigating this, and now it turns out the hardware mitigations are not fully effective and basically rendering them worthless. My understanding also, I think they sounds complaining that these hardware mitigations are rather complex. Here, those solutions are complex. And read this paper, Wonder Branch. Oh no, this is a piece of paper. And given this is a recurring theme, right? Hardware is so complex, it is not only buggy. I think we also, not even security, but we had even Intel and AMD stability. Remember the Phenom 1, I think, of a decade ago, of hardware translational local site buffer bugs, not to mention various Intel bugs. Not only 386, what was it, Push A or whatever, Pentium F00F, and some floating point, what was it, hardware divide, I think, where they had typos in their division tables. And with that, I wonder if it even makes sense to design hardware in a way to mitigate complex scenarios that a year later are found being ineffective, and not better design software in more modern ways that avoid this kind of exploitation scenarios fully, in terms of fully asynchronous and other I/O urine. Anyway, yeah, of course, as I said, yeah, history brute forcing, right? As I said, this mentioned in the beginning of this video 20 minutes ago. This is brute forcing, right? Relying on synthetic covert channel, demonstrating how they use BHI cross-privilege attacks, end-to-end exploit targets not unmodified kernel. It's no longer available since no inner workings there. So exploiting that and so on. Leave in the comments below. Yeah, full attack, same predictor, made exploit, and so on. At the end of the day, you've seen this. What was it, 960 or so bytes per. What was it? 160 bytes per second, in spite of the isolation-based mitigations. Leave in the comments below. So yeah, that is the thing. Long story short, always, if you run stuff in production, always apply latest and greatest hardware and software mitigations. There were microcode updates from Intel. Not sure if they did much to that, but as seen also here, I think this means for AMD that the AMD, so yeah, I mean, this quote is like, at AMD, product security is top priority and take security threat serious. Now, who wouldn't, right? Multi-billion-dollar industry. And following the process of coordinating with the ecosystem, publishing, resulting. I think for the AMD stuff, that means they are not, so I don't want to watch that though, that they are not using AMD red pull lines anymore. Yeah, AMD also instructed customers to switch to using one of the other published mitigations, aka generic red Poline company also publishes updated Spectre mitigation guidance reflecting those changes. And yeah, so basically what that means is that AMD mitigations immediately became significantly less performant. I think they didn't, yeah, I mean, AMD had this special AMD red Polines for better performance, just like now, yeah, not fully mitigating so much to better performance. That means that the AMD mitigations now using generic red Polines incur the same or similar performance cost as Intel CPUs previously already incurred, so much to improved AMD performance. And as I said, yeah, applies the latest security patches, and the research here continues. Your mileage may vary, and leave in the comments. For me, as I said, I wonder if implement hardware that complex that it takes multiple years to find vulnerabilities, multiple years to hardware mitigate them, and multiple years to later find that those mitigations are basically mostly worthless. I recurrently come to the conclusion that this kind of implementation are too complex for truly stable and secure computers, microprocessors going forward. I think the call would be better for less complex microprocessors. The drawback, of course, for those is less performance, right? Less complex usually means less performant. So with that being said, maybe it's time to also develop software in a more embracing, massively parallel way, so that instead of this highly speculating single core performance processors, we rather have, unfortunately, then like 30 or so % less performance on single threaded performance, but due to less hardware complexity, maybe 30%, 40% more cost or something. I think this is at times the only viable way forward, because as seen here with this complex hardware and complex mitigations, I don't get the impression that this processor, this way of developing processor cores is a viable, secure and stable way going forward. And I'm also looking forward to see how many Apple Silicon vulnerabilities we will see in the future, because Apple is having their own cores, as you know. So I wonder if where do we have this? If anyone actually has taken a closer look, and I would be surprised if Apple Silicon is not affected. I mean, if the whole industry is affected, why should Apple not be? And with that being said, what mitigation and security impact that had. Last but not least, of course, I'm aware that just adding more, like similar to the P3, right? Which obviously was not the best, and like Pentium P4 net burst architecture, very long pipeline, but certainly aware of those limitations, and certainly massive, like simpler design and more cores does not solve everything. Certainly with more cores, I think 40% more cores for in total similar performance. You have, of course, also scalability issues, hardware caches, locking and similar stuff on the bus, and so on. Not saying everything is easy or that is an easy solution, but I'm not seeing this complex attack surface and mitigations to be particularly viable in the future. And maybe also, yeah, probably next I should actually study this stuff, like fully asynchronous. Wonder how they implemented the system call stuff. Anyway, that's it for this video. I hope you learned something. Leave in the comments below what you want to see in more detail, what you learned something, or your comments to that state of security, speculation and hardware mitigations. Don't forget to like, subscribe, and hope to see you soon for the next fun stuff to come. Actually, there's one more thing common there. It's time to leave x86 and ARM. The problem is, of course, not only x86 and ARM. Right? We have seen PowerPC exhibit A. So maybe I should. Nothing like dropping at pressure. Exhibit A. PowerPC, of course, also being affected. And last but not least, so of course this RISC-V is so simple, previous video, it is probably not affected, but RISC-V is also becoming increasingly speculative. And so the problem is the microarchitecture, right? The instruction set format and decoding front end are not the biggest issue. So given a similar microarchitecture implementation, think having a RISC-V decoder front end for any of those microarchitecture implementation or future variations thereof, I don't expect RISC-V to be immune as it to that, right? So it's not really x86. Also, I would say x86 is certainly the way too complex, previous videos, right? The way too complex to be sanely and bug-free implemented. And the true story, however, is like RISC-V will not magically fix it. So the same remarks of having a potentially less speculative microarchitecture implementation for avoiding such class of vulnerabilities. And maybe it is time also to innovate, and that is the problem, right, with also x86 and ARM legacy. Use something like RISC-V to innovate for more high performance, modern yet speculation mitigation system call implementations like IOU ring or kernel different modern task privilege level switching or isolation implementations for microkernel performance and in general avoiding this class of mitigations. So yeah, but that was one more thing. See you next time.